In this problem, what we have is a bullet B, which is traveling to the left with some known speed of VB1. It strikes a stationary block A. However, here when the bullet hits A, it doesn't stick. It actually goes through A and comes out there on the left-hand side. What we know is that after impact occurs, we know that the block A will slide to the left through some distance of 2.7 meters. And what we want to know is what's the kinetic coefficient of friction between A and that surface that allows A to come to rest in that distance. What I'm going to do is break this up into two segments of time. Between time 1 and time 2, we're going to say that that's during impact. And if I look at the FBD of A and B together, and although I'm showing it right when B is getting ready just to strike A, this FBD is true for the whole time during which impact occurs. The point being is together, although there's a lot of force going on of A on B and B on A, as a whole of A and B together, there's no net force in X. So this says that linear momentum for A and B together is conserved. Okay, so the notation I'm going to use here is MA and MB, I guess, for the masses. So MA VA1 plus MB VB1 is equal to MA VA2 plus MB VB2. A is initially at rest. The left-hand side, since B is moving in the negative X, I'm going to put a minus sign there in front, and that's equal to that. We also know what VB2 is doing after impact. So I can carry through on the right-hand side by writing this as MB minus VB2, whatever, that's a known number. So what we can find here is VA2, its speed after impact occurs, is going to be equal to MB times VB2 minus VB1 divided by MA. So this is what block B does after impact. It's going to be moving to the left, and it's going to have that speed. But what we want to find out is once the impact is over with, we want to relate the distance that slides before it comes to rest back to the coefficient of friction. So if I look at A by itself now, this is after impact 2 to 3. The force is acting on A. Well, there's going to be weight, normal force, and since the block is sliding to the left, the friction force then is to the right, and that's equal to mu sub Kn, which is mu sub K MAG, like that. So here is where I'm going to use the work energy equation, because that's a good one to use, because it relates the distance traveled back to the change in energy. So if I write down T2 plus V2 plus the work done from 2 to 3, non-conservative, is equal to T3 plus V3. Well, there's no change in potential. A is moving along a horizontal line, so there's no change in V. We're looking at A coming to rest, and I should say this is just for A. So A coming to rest, so T3 is a 0. So T2 is 1/2 MAVA2 squared. We just found that. The work, well, that's going to be friction force times the distance d with a negative sign in front. The negative sign is important here because this is saying that this opposes the motion. So therefore, what we have here is 1/2 MAVA2 squared is equal to FD. F is equal to mu sub k mg, and this is times d. This is MA because we're just looking at A. MA cancels out. So the coefficient of friction, kinetic coefficient of friction that we need then is equal to VA squared, VA2 squared, divided by 2GD. And VA2 squared we saw was MB or MA, the difference between the final and initial speeds of B. And so this whole thing gets squared, divided by 2GD. So the important thing on this problem here again was to break it up into two parts. During impact, A and B together, momentum is conserved. So that tells us what A is doing after impact. A little bit different than some of the problems we have done here, though, in that we're not making any assumptions on sticking. In fact, we know A just goes, the bullet goes right through A, and we know the speed of B before impact, the speed of the bullet after impact, and that is what allows us to get the speed of A after impact. After impact, we'll use the work energy equation. It starts out with the kinetic energy of 1/2 mv squared for A. The work done is negative because friction opposes the motion. And the final kinetic is a 0 because we're looking for the maximum distance that it travels to the left. And so from that work energy equation we can back out what that coefficient of kinetic friction needs to be.